You know, when you look around, our universe is in constant motion, from these giant swirling galaxies all the way down to the wheels on your car. But here's the thing, it's not just moving from point A to point B, it's spinning. And today, we're going to dive into the incredible physics behind that spin. So, what on earth could a massive spinning planet possibly have in common with a little toy you hold in your hand? Well, it turns out they both follow the exact same rules, the physical laws of rotational motion. And by the time we're done with this explainer, you're going to understand those laws and see just how they shape literally everything around us. For the longest time, to make life easier, physics treated almost everything like a point particle, just a single, tiny, dimensionless dot. Now, this was awesome for figuring out how things move in a straight line, but it was missing a huge piece of the puzzle. Because let's be real, the world isn't made of simple dots. It's made of actual complex objects. Things like rods, disks, you name it. And these things do way more than just travel from A to B. They spin, they tumble, they turn. And this is where that simple model just falls apart and where the really fascinating physics begins. Okay, so all motion can really be broken down into two main types. On one hand, you've got translational motion. So imagine you move a rod, keeping it perfectly flat. Every single particle in that rod is moving in the same direction at the same speed. Simple enough. But what if you pin one end down and swing it? Now you've got rotational motion. Here, different parts of the rod are moving in totally different directions, but they're all circling around one central point, or axis. Now, to study all this spinning stuff without going crazy, physicists came up with a perfect idealized concept, the rigid body. Basically, it's an object that doesn't bend, or stretch, or deform at all while it's moving. Think of a solid steel rod or a bicycle wheel. This idea, this rigid body, is going to be our main character for this whole explainer. Okay, so we've got our rigid body, but what makes things spin? Or maybe a more interesting question is what makes them resist spinning? Because it turns out every object has its own kind of personality, a certain stubbornness when you try to get it to rotate. I mean, think about it, right? You can flick a pencil and get it spinning in an instant, no problem. But try to get a heavy bicycle wheel spinning just as fast. Yeah, that's going to take a whole lot more effort. Why? They're both rigid bodies, but they behave completely differently. The answer has a fancy name, moment of inertia. But don't let the name intimidate you. All it really is an object's resistance to being spun. You know how mass is an object's resistance to being pushed? Well, moment of inertia is just its rotational equivalent. It's basically a measure of an object's rotational laziness. And this is the absolute key. Once something is spinning, it really wants to stay spinning. The perfect example? A ceiling fan. When you switch it off, it doesn't just stop dead, right? Of course not. It keeps going for a while, just coasting on its own inertia. That stubbornness, that's its moment of inertia in action. So this leads us to the next big question. If objects are so stubborn and they resist being rotated, how in the world do we get them to spin in the first place? What kind of force does that? Well, it's not just about pushing or pulling in a straight line. Nope. To make something rotate, you need a very specific kind of force. You need a twist. And in the world of physics, we have a special name for this twisting force. We call it torque. The absolute best way to get a feel for torque is with a simple door. We've all done this. If you push the door near the handle, far away from the hinges, it swings open nice and easy. But now, try to apply that exact same push right next to the hinges. The door barely budges. The force is the same, but the torque is completely different. And that proves it. Torque isn't just about how hard you push, it's all about where you push. So, let's put it all together. We have moment of inertia. That's the object's stubbornness, its resistance to spin. And we have torque. That's the twisting force that makes it spin. These two concepts are the bedrock. But why do they matter so much? Well, because together they explain the mechanics of pretty much everything that spins in the universe, from planets to pirouettes. And this isn't just some abstract thing for a textbook. It is literally everywhere you look. The spin of our planet gives us day and night. The torque in your car's engine is what makes it go. The incredible stability of a moving bicycle. That's all about the rotational physics of the wheels. And get this, when you see a figure skater pulling their arms in to spin crazy fast, what they're actually doing is changing their moment of inertia on the fly.
These principles are just fundamental to how our world works.
So, the big takeaway here is that this stuff isn't just for physicists in a lab. From the cosmic dance of galaxies to something as simple as opening a jar of pickles, these principles of rotation are always at play. And understanding them gives you a much deeper appreciation for the beautiful mechanics of the world.
And that leaves us with one final, kind of mind-bending thought. Rotation is so fundamental, it's so woven into the very fabric of existence, it just makes you wonder. If every planet, every galaxy, every single atom just stopped spinning for this 1 second, what would actually happen? It's a question that really makes you think about the incredible, invisible forces that are holding our entire universe together. Thanks for joining me on this one.